It's my very great pleasure now to introduce Dr. Ramachandran. He is the director of the Brain and Cognition Center at UCSD, and he's also, of course, hugely participating at the Salk Institute. He's been named by Newsweek as one of the top 100 people to watch in the next century, and was named by Richard Dawkins the Marco Polo of neuroscience. Please welcome Dr. Ramachandran.
What I do is research on the human brain. So let's pause for a minute and ask ourselves what we're dealing with. So inside the cranial cavity, there's this lump of flesh, 3 pounds, weighing 3 pounds. And this lump of flesh asks questions about interstellar space, the vastness of interstellar space, asks questions about the meaning of infinity, asks questions about itself asking questions and its own place in the cosmos. And how does this come about? It's 100 billion nerve cells firing away in the brain, creating a whole spectrum of abilities we call human consciousness or human nature. So my approach has been to look at lesions in different parts of the brain producing characteristic changes in behavior. What you get when there's a lesion is not just an across-the-board reduction in all your mental capacities, but often a highly selective loss in one mental ability with relative preservation of other abilities. So that gives you some confidence that that region of the brain is specialized for that function. Now in today's lecture, what I like to do is to focus on 3 aspects of human nature which we regard as unique and human beings are especially good at. Perhaps we're the only creatures even capable of it. One is humor and laughter. Okay, what is the brain basis and evolution of humor and laughter? And the second question would be empathy and the origin of civilization, culture and civilization in humans. And the third question would be creativity, what makes us creative? And I'm going to cover all that in the next 20 minutes. Okay, let's first talk about, let me begin with empathy and human nature. Or let me begin with humor, okay? It's always fun to do. So humor and laughter, let me begin with a patient named Mickey, who I saw not long ago. And I was doing a routine neurological testing on this patient, testing her touch sensations, touching various parts of her body, and it was all completely normal. Mentally, she was normal, fluent in conversation, attentive, everything was fine. Then I poked her with a needle as part of the neurological exam, different parts of her body. What do you feel? Ouch, that hurts. Don't poke too hard, okay? So she said, that's painful, that's painful. And then many patches of body, when I touched her, she would say, ha ha, and she'd start giggling like crazy. So here's a human being laughing at the face of pain. It's the ultimate oxymoron. How can a person laugh when poked with a needle, right? So why does this happen? It got me start thinking about humor and laughter in general. Why did humor evolve? If a Martian ethologist was watching all of you here in the audience, every now and then you'd stop and start shaking your head and making this funny ha 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 noise. And you'd be extremely puzzled. Why does this happen? Why do humanoids do this? So I started thinking about this, and then I realized that, first of all, it's probably universal. It's probably hardwired in the brain, because every culture, every civilization, every country has some form of laughter and humor, except Germans, okay? And among animals, of course, there's no humor, but of any kind. So the question is, given it's hardwired in the brain, why? Why does it exist? Well, when you look at humor and laughter, you see it has the following form. All jokes, humorous incidents, humorous narratives, you lead the person along a garden path of expectation. And at the very end, you're building up a story, you introduce a sudden twist or punchline that entails a complete reinterpretation of all the previous data. And that's what you call humor. Now that's necessary, but it's not sufficient. Supposing this guy is building up an elaborate scientific theory, and you prick the bubble and you say it's wrong, and it entails a complete reinterpretation, he won't think it's funny, okay? Believe me, I've tried a lot. So what makes it funny? Okay, let's take slapstick. A chap is walking along, preferably a portly, self-important gentleman, walking along the road. There's a banana peel and suddenly slips and falls down. Okay? So you're building up an expectation that the gentleman will reach his destination, but he doesn't, he slips on a banana peel, falls down. Now if he falls down and cracks his skull and blood starts spilling out, you won't laugh. Hopefully not. You'll go and call the ambulance, or you'll rush to his aid, tell people rush to his aid and all of that. But supposing he slips on the banana peel, falls down, and then wipes it off and looks all around him. Then you start laughing. It's the basis of all slapstick comedy. So what's the key difference between the two scenarios? The key difference is in the first case, there's been a genuine alarm. Your alarm bells start ringing. Genuine danger. So you call the ambulance, you do something appropriate, you orient. In the second case, your brain realizes this is a false alarm. And you don't want people rushing to his aid and wasting their energy and resources. So this is your nature's false alarm bell. By laughing and producing a characteristic sound, you're telling everybody, your kin, who share your genes, don't waste your resources rushing to this chap's aid. So this is my theory. Now, how do you test this? Let's go back to my patient, Mickey, who used to laugh and giggle every time I poked her. How do you explain that? Well, you go and look inside her brain. It turns out there's an area called the insular cortex in the temporal lobes, on the sides of the brain, and that insular cortex sends projections indirectly to the anterior cingulate. The insular cortex is the region of the brain that receives pain, the sensation of pain. The pain sensory signals go to the insular cortex. And then there's a wire that goes from there to the anterior cingulate, which experiences the agony of pain. Ow! Okay, so pain, in fact, we think of as a single thing, but in fact has many steps involved, many stages, many layers of pain involved, starting from mere sensory signals all the way to the subjective experience of agony, the aversive quality of pain. Now that wire was cut in her. So what's going on in her brain? Initially there's an alarm, potential alarm saying, hey, something painful is coming in. The very next second, the anterior signal is saying, but nothing is happening. It's not painful. The two ingredients are in place, a potential alarm, then deflation of alarm saying there's no danger, and the guy starts giggling uncontrollably. So here is an aspect of human nature, namely humor, which you would think is inaccessible to experiments. You can do an experiment, show these pathways are involved in the brain, and also tell you about the evolution and perhaps the function, all of that in one single patient, right? Now we still don't know if this is true or not, but you can do brain imaging to test it. Now the other thing, of course, is tickling. Same sound you produce. Why would there be tickling? Well, think of what happens. The menacing adult approaches the child about to do something nasty, and they say, chick, 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 chick. And I don't mean anything. So again, there's a potential alarm and the deflation of the alarm. And I think tickling is rehearsal for adult humor, okay, so to speak. Now, what other situations do you laugh? And that's a whole lecture. I won't go into it. The second part of the lecture was about creativity. How do you study creativity? Now, we latched onto this when we saw a phenomenon called synesthesia. And this is first reported by Francis Galton, who was Charles Darwin's first cousin in the 19th century. And he noticed that some people who were completely normal otherwise had the following peculiarities, following quirk in their brain. And that is, every time they saw a particular number, the number would be tinged with a particular color. So 5 is red, 6 is green, 7 is blue, 8 is chartreuse, 9 is indigo, and so on and so forth. And sometimes tones were colored. C sharp is blue, F sharp is green, and so on and so forth. Now, why would this happen? Now, one of the first things I did was, hey, this chap is saying numbers are colored. Okay, what if I give him, instead of Arabic numbers, I mean, actually I call them Indian numbers. They come from India. So you take Indian Arabic numbers. Instead of that, you show him Roman numbers, V or V1 or whatever. What does he see? Colors. An obvious experiment. And he says, no, I don't see any colors. So what this is proving is not the numerical concept of sequentiality, ordinality, cardinality is driving the color. It's the visual appearance of the number. So we started experimenting on this, and we found that there's a structure called, next slide? Thank you. Next slide. They're just showing you neurons. You all know about it. Next slide. Maybe we'll leave it there. Okay, next slide. Sorry. Skip all that. It's all phantom limb stuff. Skip all that. Sorry. Keep skipping. Keep skipping. Sorry. It's another lecture here. Keep skipping. You should get to a point where it says synesthesia. Okay. Next slide. Next slide. Sorry. Next slide. This is going to take up the entire talk. Next slide. Next slide. 2 more slides, and there's a brain image. There it is. Okay. If you take a slice through the brain, a coronal section, what you find is the number area is right there, the red circle. It's in the fusiform gyrus of the brain. And the color area is also right next to it in the fusiform gyrus of the brain. Then I said to myself, what's the likelihood that these two areas, color and number, are almost touching each other in the fusiform gyrus? And the most common form of synesthesia is number to color. Maybe there is some sloppy wiring here. Every time he sees a number, he sees a color. Also, in the fusiform, it's the visual appearance of the number that's represented, not the high-level concept. So that fits the observation that Roman numbers don't evoke colors. Okay? All right, so far so good. Now, how do we prove this? We'll do a whole bunch of experiments, but mainly we did brain imaging. If you take a normal person, show him numbers, number area lights up. If you show a normal person colored numbers, number and colored area lights up. If you show a synesthete, black and white numbers, number and colored area lights up. Not only that, people have now done diffusion tensor imaging and actually wires, cross-wiring between these two areas. Now you say, well, what's all this got to do with creativity and all that? First of all, you have to ask yourself, why does this happen? Why do some people have this quirk? What I found was, contrary to previous claims, 1 out of 50 people has this condition. So there may be 1 or 2 of you here who have not come out. Okay? So 1 out of 50 people has synesthesia. Now, why would 1 out of 50 people have this condition? Well, the secret comes from the fact that in the fetus or in the infant brain, everything is connected to everything. I mean, that's not strictly accurate, but there's a tremendous redundancy of connections in the brain. And as the brain develops, the excess connections get pruned away to create the characteristic modular architecture of the adult brain. Okay? Now, this is done by pruning gene or pruning genes in the brain. Supposing there's a mutation of the pruning gene, then you get inadequate pruning between adjacent brain regions. And if some of the genes are expressed selectively in the number-color region in the fusiform gyrus, then you're going to get excess connections between those regions in the fusiform gyrus, namely number and color. So every time he sees a number, he sees a color. Now you say, what's this got to do with creativity? Well, it turns out, people have known for a long time, synesthesia is about 7 times more common among artists, poets, and novelists than in the rest of the population. People didn't know why. In fact, the common ideas about synesthesia, since the time of Francis Galton, there have been several theories about this. One theory is they are acid junkies and potheads. They're on drugs. And there may be some truth to this because they're much more common at SDSU than UCSD here. But jokes aside, you do see synesthesia under drug use, so it's not a silly idea. But not all of them. Most of them, in fact, are not on drugs. So you have to explain that. Another theory is maybe they're just being metaphorical and they say 5 is red and 6 is green and all that. Anyway, I'm not going to go into all the theories, most of which don't make any sense. So we had a very simple theory which is based on this cross-activation or cross-wiring and the genes being mutated, causing excess connections. And if the gene is selectively expressed in the fusiform, which can happen because of transcription factors, then you get number-color synesthesia. If it's happening somewhere in the auditory areas, you get auditory color synesthesia. What if the gene is expressed throughout the brain? Right? This defective pruning gene is expressed throughout the brain, and different concepts and ideas are also in different regions. A lot of evidence for this. Just now I told you arithmetic or numbers are here. The fusiform, arithmetic, high-level arithmetic, multiplication, all of that is in the angular gyrus, higher up in the brain. What if ideas and concepts are also in the different parts of the brain, and there's greater connections between different parts of the brain? Your brain, there's greater propensity to link seemingly unrelated ideas. And what do you mean by that? You mean creativity, you mean metaphor. Like, what's a metaphor? Take an example from Shakespeare. It is the east and Juliet is the sun. What does that mean? Juliet is the sun? Does that mean she's a glowing ball of fire? I mean, actually, schizophrenics say that. But that's another lecture. If you take most normal people, they'll say it means Juliet is warm like the sun, radiant like the sun, nurturing like the sun, rises like the sun rises in the east, rises in bed or whatever. Right? So your brain instantly forms all these links, and Shakespeare, of course, was a master at this. Now, so what I'm arguing is these people have excess connections, creating a propensity to link seemingly unrelated ideas, hence a propensity towards metaphorical thinking and towards creativity. So now you could say that's the reason this gene survived. If there's a useless gene, a gene that makes you see 5 as red, why would it persist in the population? 1 in 50 people has it. It would have been weeded out a long time ago through genetic drift, through natural selection. But it's still present. Why is it present? Because it makes some outliers in the population creative and metaphorical. Now, when I say this, people in the audience often ask me, if it's that good, if the synesthesia gene is making you creative, how come you don't all have it? Well, that's a silly question because evolution takes time. Maybe another 100,000 years, everybody will have the synesthesia gene. But the more important reason is you don't want everybody to be metaphorical and creative. Right? I mean, if there's a neurosurgeon doing surgery on your brain, you don't want him getting metaphorical on you. Okay? So you want surgeons to be perfectly straight-laced, focused, and all that. So to preserve the heterogeneity of personalities and creativity, that's why you don't see it in everybody. Okay. Now I'm going to move on ahead to the third section of my talk. We talked about humor and laughter, the evolution of humor and laughter, the purpose of humor and laughter in humans, what purpose, function it serves, and what the neural basis might be of humor and laughter and of tickling. Even smiling, by the way, may have the same origin. Somebody comes to you and smiles in a social situation. Why? He says, I'm a pal. I'm friendly. Now, how did this evolve? Early in evolution, when you bare your mouth, you show your teeth, your canine, saying, I'm aggressive. So when the alpha male is coming towards you and does that, it means he's aggressive. And you take defense and you worry about what's going to happen. So there's a potential threat and alarm. But if that guy comes and he wants to tell you, no, I don't mean any harm, he aborts the aggressive gesture halfway. The net result is a smile. He says, I don't mean any harm, I'm your pal, you know me. So deflation, potential alarm, deflation of alarm, that's why a smile has the same subjective quality as a laugh. You could think of it as a lesser laugh. It's again about deflating alarms. Okay, I'm going back and forth here because of the time limit. Let's go to the emergence of civilization in humans. And a lot of it occurs because in early civilization, in the birth of civilization, it was done through imitation. What do I mean by culture and civilization? Supposing you have a polar bear, it has to evolve a coat for the winter. It took about 400,000 years to evolve that coat. A human child watches his mother slay a polar bear, skin the polar bear, put it on. And just maybe half a dozen times it watches it, maybe a little bit of practice, it learns it. So evolution, from being natural selection and genes, became Lamarckian. Right? It became acquired in one generation what would have taken several hundred or several thousand generations. Now, the key question then is, how does the child imitate the mother? Because once it imitates it, it spreads like in geometric proportions, spreads like wildfire, both vertically, parent to offspring, and horizontally, other peers in the group. And that's the origin of culture. So how does it come about? Okay, it turns out that the answer comes from phantom limbs, believe it or not. One of the things we study is patients with an arm amputated, and they have a vivid sense of a persisting phantom arm, right? Now, why does this happen? We have an elaborate theory of why it happens. We've developed a cure based on putting a mirror, and the guy looks at the reflection of the normal hand in the mirror, so we resurrect visually his phantom. If you move a normal hand, the phantom looks like it's moving, often relieving his pain. Now it's widely used in clinics all over the world because it's been tested, double-blind, placebo, all of that. Okay, but let's go back to phantom limbs. One of the astonishing observations made in recent years is a group of neurons called mirror neurons in the brain. We all know there are neurons in the front of the brain which fire when you make a movement, when a monkey makes a movement. When a monkey reaches for a peanut, one neuron fires. When he reaches and pulls a lever, another neuron fires. If it pushes something, a third neuron fires. These are called motor command neurons, discovered by Vernon Mountcastle about 50 or 60 years ago. They're very, very well known. Okay? So they're programming a set of muscle twitches to make the appropriate semi-skilled movement. Okay, but about 10 years ago, Giacomo Rizzolatti in Parma in Italy discovered something amazing. A subset of these neurons, say there's a neuron that fires for moving and grabbing a peanut. A subset of them will fire when the monkey watches another monkey reaching out and grabbing a peanut. This is absolutely astonishing. It's like this monkey is taking the other monkey's point of view of the world. It's doing a virtual reality simulation of the other monkey, adopting the other monkey's vantage point, and putting itself in the other monkey's shoes, so to speak. And now we have shown that this exists in the human brain too, mirror neurons. Okay, so it's like a mind reading neuron, monkey see, monkey do neuron. Okay, and they exist in humans. Now another type of mirror neuron is for touch that was recently discovered. If somebody touches me, there's a whole map of my body surface on my brain, and one of the neurons fires. If you touch me here, another neuron fires. If you touch me here, another neuron fires. Astonishingly, about 10% of these neurons will fire if I watch you being touched. Okay? So the question then becomes, if these neurons, which you can call empathy neurons, right? Because they're starting empathizing, I'm empathizing with your touch signals. If the neuron fires and I simply watch you, why don't I actually feel the touch? The same neuron is firing if somebody touches me or touches you and I'm watching you. Why don't I get confused and say, hey, stop touching me? Or somebody pokes you with the needle, why don't I say, ouch? Okay? Why doesn't that happen? Well, the answer, it turns out, is you've got a normal skin, so I'm watching you being poked. My mirror neurons are firing. Strictly, they should make me feel you being poked. Doesn't happen because my normal skin receptors are sending a null signal, saying, don't worry, you're not being poked. And they're inhibiting part of the mirror neuron output, so empathize by all means, but don't feel the pain, okay? Because you're not actually in pain. Don't worry. Your skin's not being destroyed. So think of the implications. Okay, now what happens if the arm is removed? Or you just inject the arm with an anesthetic, completely removing the arm signal. The astonishing thing is this person now experiences touch sensations delivered to other human beings. He literally experiences it. If you poke him, he says, ouch, it hurts. Okay? So we call these hyper-empathy syndrome, we call them Gandhi neurons. Okay? Because basically they're dissolving the barrier between you and other people. It's not Eastern mysticism. These neurons are like Facebook or internet. They don't know bloody difference whether he's being touched or you're being touched. And I'm not talking in some metaphorical, abstract sense. Quite literally, the neuron doesn't know. Okay? So what I'm arguing is these neurons emerged initially to allow adopting another person's vantage point, which is absolutely critical for imitation. If you want to emulate or imitate what somebody's doing, you have to adopt that person's point of view. In fact, we've shown also that they're deficient in autistic children. And that may be one of the key deficits in them. They're not able to adopt another person's point of view or empathize with another person, although in other cognitive skills they may be okay, especially high-functioning autists. So once mirror neurons went in place, and I don't mean just mirror neurons are enough, because monkeys have them, they're not the proud bearers of a civilization. But once they got going, they got hooked up to other brain regions, like inferior parietal lobule, frontal structures, and this got us all going on the path towards becoming completely human and all the other attributes that we treasure and cherish. Thank you.